Everyone, today I'll be explaining today's code, which is 9701 22 October November 2015. Anyway, let's start. Fill the gaps in the table for each of the given particles. So they gave you a table which is half full. So for carbon 13, you see here that there is how much? 4, so there are 6 electrons from the electron configuration. So we know that the carbon 13 here, they gave you the mass number or the nucleon number. And since the number of electrons here, which is 6 electrons, is the same as the periodic table carbon, so it means that the charge should be 0, so there is no change in the electron number. So we can then deduce that it is an atom, not an ion to be a cation or an anion, so it's supposed to be an atom. Symbol, the mass number should be up, and the atomic number or the proton number should be down. Okay, now you have for chlorine, but the first thing you'll notice that it has a charge. So if it has a charge, it should be an ion, and now they want you to specify whether it is a cation or an anion. So if it was negatively charged, anion, positively charged, cation. Okay, I know I'm spelling them wrong, but who cares? So an anion. Now nucleic acid up first thing. As I said, mass number, proton number. So electron configuration is basically, since there is minus, means that electron number had increased by 1 from the proton number. So it's basically, we have basically 18 electrons instead. So put the electron configuration 1s2, first shell, 2s2, 2p6, second shell is done, 3s2, 3p6, this is the third shell, and that's fully the 18 electrons of chlorine. Now we basically copy whatever they did, chlorine, and then you notice that T13 was the mass number of carbon, so we'll do the same thing for chlorine. The mass number of chlorine, where we got it from here. Alright. Next part, we have here sulfur. They gave us its mass number. And then atom means that the electrons are the same number as the protons. And here it shows 0 charge. Okay, now the symbol, first thing the S, and then the mass number they gave you, which is 34. Now the proton number is based on your periodic table. You're gonna check from the periodic table, you're gonna see it's 16. Now electron configuration is gonna be 16, just like the protons, because there are no charge, so the electrons are not affected. So again, you write them. 1s2, 2s2, 2p6, 3s2, 3p4. Good job. Now same thing for iron, 54 mass number. Cation mean it is a positively charged ion, so you can now do it. Now if you counted the electron configuration, if you counted them individually, like 2 plus 2 plus 6 plus 2 plus 6 plus 6, you'll notice that you have 24 electrons. Now if you check the periodic table of iron, since the proton number never changes, you'll notice that the proton number of iron here is 26. Now if you compare it with the electron number that we found it from the electron configuration, is 24. So yes, it is a cation, but by how much? by 2 plus charge means that the proton number have been reduced by 2 to give you 24. That's exactly how we found it now. Write Fe for the symbol, the mass number, they gave you 54. The proton number never changes, but that is not how we finish. We still need to show that there is a charge, 2 plus. Alright, hopefully understood. Now, part B. All of that explain the meaning of the term electronegativity. That is very important. Okay, electronegativity is basically where, maybe give an example, you have here an HCl. Cl is more electronegative than H. It will be like, give me the electron pair I wanted. So it means that exactly what electronegativity is, that chlorine has higher electronegativity than hydrogen, so chlorine is the most powerful one. Alright? So you can, I'm sorry. Oh whoa, what's going on? Sorry. So you can write now, it is the tendency or the ability, what's going on? It's the ability or power of an atom or a nucleus. As you know, it's a nucleus of the chlorine that actually attracts the opposite charged electron, but you can say either atom if you want, or nucleus, to attract the electrons which are this. Alright, and now that's the first mark, as there are 2 marks for this question. The other mark is it is in a covalent bond. Which is very important because here, for example, this is a covalent compound. Okay, so very important. Alright, name and describe the type of bonding you would expect to find between particles with equal electronegativities, which is actually very important. How you might get confused. First thing, in covalent bonds there are polar and non-polar. And basically the polar are the charged ones, you could say. Charged. Okay. And this is none. And let's say an example of a polar. Again, that was an example of a polar. Now we'll get why. HCl. When there's a polar, as I said, there are negatively charged, there are oppositely charged ions, right? Or charges, you could say. How that the Cl is more electronegative than hydrogen. So it will attract the electron pair to give Cl minus and the H plus. So what is this called? It's basically called heterolytic fission, which means that when this happens, basically they are not equal. The electron share not equal. By the way, again, I'm sorry for the bad handwriting. Now, for non-polar, I'll give you an easy, which is actually like my, okay, a Cl2. Now, you'll notice that Cl and Cl, they're basically the same atoms, right? So, the key word is same electronegativity. So now you'll notice here Cl had higher electronegativity than hydrogen, so they did not have the same electronegativity. But in the nonpolar case, like the Cl2 or I2 or whatever you're gonna say, they have the same electronegativity. So the Cl won't be like, I want this or I want this. No. Like, I mean, like the Cl, like one Cl won't be like, I will attract it and you will become plus. That is so wrong. Since they both have the same electronegativity, they both attract this pair of electron in the same exact force. How? Cl, Cl. So, since they both have the same power, the Cl will be like, I want one electron. Since there's two electrons, right? Let me change it a bit so you guys won't get confused. Since there are like an electron pair, there's two electrons, right? So Cl will be like, hey, I want one. And the other Cl will be like, hey, I want one. To give you one Cl radical, another Cl radical, which means that one Cl has only one unpaired electron and the other Cl has one unpaired electron. This type of reaction is called homolytic fission. Alright? The polar, like the HCl, was heterolytic, and the non-polar, like ClCl, Cl2, is homolytic. Alright, so these are the equally shared electron. These, they do not equally share the electron. Hopefully understood. Alright, so, and now on this question, since they are asking about the type of bonding, first you're gonna say it is a covalent bonding. Because, wait a minute, it's a covalent bonding. Why? Because like basically only covalent bonding that actually can equally share the electrons, which has equal electronegative, like ClCl. And now they said to describe how, basically by sharing electron pairs, that's basically it. Alright, now basically we said it's just sharing electron pairs, because they did not actually ask that much about it, just said to describe the bonding, which is covalent, and how, which is by sharing electron pairs, which basically both of them has sharing electron pairs, but one of them shares equally and the other not equally. That's it for 2 marks. Now name and describe the type of bonding you would expect between particles with very different electronegativity. Now some of you people would say, yes, not polar again. But here they mentioned that it has like a very different electronegativities. Now they mentioned it has very different electronegativity. So an easy answer that we just give you the marks. Ionic. Because ionic compounds, for example, in ACl, always there must be a Cl minus and an A plus. Do you understand? So basically they always give you charged ions, and they for sure have very different electronegativity. So ionic is the answer. And now describe how. You say the electrostatic attraction between oppositely charged ions. Alright? Hopefully understood. Now we have C. The boiling points of some molecules with equal number of electrons are given. Explain where the boiling point of fluorine and argon, are so similar. So let's check it out. So basically when you always talk about boiling points, you immediately think that they're talking about the intermolecular forces, and if you want to be exactly talking about the London forces, which are the ID induced dipole forces. That's to be exact. But basically, we have here between fluorine and argon, you see that they nearly have the same boiling point. And you can just like here write about similar strength of intermolecular forces, van der Waals forces or London forces. Van der Waals forces are basically all the forces like you can see in here, which are not actually you're forced to suggest which. Now, for example, fluorine here, it's a nonpolar, and nonpolars have ID. Now, basically, every single compound has ID. I just want you to remember every single compound have ID. Alright? So, intermolecular forces, again, they are. Or you can say the van der Waals forces are ID, which are in nonpolar molecules. Example, what do we have here? F2. Alright? Then you have PD, permanent dipole, which are in polars. Again, example, HCl. Basically, covalent, please. Don't you ever think they go in ionic, it's always covalent. Last one, the blue color. The hydrogen bonds, like OH and H2O. Alright? Now, now just you can write that they have similar strength of, similar strength of intermolecular forces. So, similar energy needed to break their bonds. What do I mean? Let's talk about fluorine, for example, so you won't get confused. This is a covalent bond. There are two molecules of F2. Again, covalent bond. But this is an intermolecular force. For example, you can say ID. Do you get it? So they both, they both have the similar energy need to break the bonds, which are the intermolecular forces. So basically, if you want to break it, you break this, not this, that's so wrong. Not the covalent bonds, the intermolecular forces. You break this. That's why when I said when you're talking about boiling points, basically talk about intermolecular forces. So it's this. Alright? Hopefully understood. Okay. Double I. Explain why the boiling point explain why the boiling point of hydrogen chloride is higher than fluorine. So we're talking about chlorine and fluorine. Where's chlorine and fluorine? Hydrogen chloride. I'm sorry, some dude keeps on beeping outside, I don't know why. Hydrogen chloride and fluorine. Alright, so first thing you can see that Isa told you HCl is a polar. As I said, polars have permanent dipole, PD. And again, fluorine has only ID. Get it? Hopefully you do. So actually this explains everything. HCl, which is polar, has PD with permanent dipole. Chlorine, which is non-polar, has induced dipole. And that's still not 2 marks, because you need to again explain this single part. Always, alright? So, HCl has or needs more energy to break its bonds, which are the intermolecular forces. Hopefully understood. Explain why methanol. Now that is always an easy question, because you're gonna say no, has the highest bond length. Let's change the color. Well, methanol has the highest boiling point among all of these molecules. Why? Methanol, like H2O, because H2O has this, which is the hydrogen bond. The OH, basically the same thing in methanol. CH3, OH, and OH is the strongest force among all the intermolecular forces. Okay? Strongest among all the PD and IDs. That's why it has the highest boiling point. Hopefully understood. Hydrogen bonding, first mark is to name the bond. Hydrogen bond is stronger than other intermolecular forces or van der Waals forces. Van der Waals force is basically another name for all the forces. Van der Waals. Alright, and please, London forces are only for the IDs. Like, just don't go calling London forces for all of them. No, this is London forces. Alright, explain the meaning of the term standard enthalpy change of reaction, which is actually very so wrong. Very important. Basically, we know how to start it. Enthalpy change when the amount or moles of reactants as shown in equation, which is actually very important, react to give the equation's product. And that's the first mark. The other mark I'm gonna get it by, should always mention this, by the way, measured at, basically the reactants should be measured in standard conditions. Alright. Basically, the enthalpy change of reaction is basically they will give you a reaction. So that's why change of reaction is based on the equation that they gave you, alright? So that's why I should always mention the equation. Alright, so part B. The enthalpy change of hydration of magnesium sulfate can be calculated by carrying out two separate experiments, right? First experiment, 45 g of water. Great, so they gave you the mass of water was weight in polyester, 3.1 g of MgSO4 was added. This third item was completely solved, okay, right. And they give you that temperature change from 23.4 to 34.7. Do you want heat energy? Alright, sorry. You can assume the specific heat capacity. They gave you C equals 4.18, which you should learn, but they gave you it this time. But please learn. Now, since they gave you want the heat energy and they gave you the capacity, so you know it is this equation. E equals mCt. E is the energy which you should find, M is the mass, C is what they gave you here, 4.18, T is the temperature change. Temperature change means that basically whatever they gave you, you defer them. You minus them from each other, so 34.7 minus 23.4. 4.7 minus 23.4. 11.3. So you found it for T. C is given, mass is now what you want. So I wanted to know, in this type of questions, you only talk about the solvent. But solvent. So I know some of you will say 45 plus 3.01, but that will affect the answer, which is wrong. In this type of questions, you only talk about the solvent, which is in this case is the water, so you only use the mass of water. Hopefully you understood. M 45 multiply C, they gave you 4.18. The change you did just now, 11.3. Now let's check. 45 multiply 4.18 multiply 11.3. Great, that's the answer. 2125.53. You basically go and put it here. Good job. Calculate the amount in moles of MgSO4 dissolved. That is a straightforward question. N equals M over MR. M is, since you did not use it the first part, now we're going to use it, so that's cute of them. 3.01. 3.01 divide the MR of MgSO4. If you just add them all together, you're going to get 120. So if you put them in a calculator, you will get the answer, in fact, 0.025 moles. Hopefully understood. Part I. Calculate the enthalpy change of solution MgSO4. So do you want the enthalpy change? Alright, include the sign is always important. Now there's this equation. Enthalpy change equals energy over moles. Now great, we have the heat energy calculated. Let's put it down, wait a minute, to 5.53 moles. As you solved it once again, you want the moles of whatever you're asking for. They want for MgSO4, which you found, which is great. Okay, 0.025. Now I just want to put them 2125.53. Great, divide 3.025. Great. How much you got? You got 85. Now do you want the signs? Alright, now you won't know what is this sign, but yes you can, because you have a trick. This. So what do you notice? You see that there is an increase of temperature. So a new rule, it's too much to write. When there is an increase of temperature, exo when there becomes a decrease of temperature. Endo. So exo is negatively charged, endo is positively charged. So since, where am I going? So since there is an increase from 23.4 to 34.7, I'm sorry, wait a minute. Hopefully not gonna come for me. Great, sorry. I meant here. Again, when there is an increase in the temperature, means it is an exothermic reaction, so it must be negatively charged. And I'm sorry for the confusion. Oh, there's a lot, that's great, wow. Anyways, in a second experiment, the enthalpy change of solution of the hydrated MgSO4 was calculated and found to be all white, so what we would find here. Alright, so use the equation below for the hydration of 100. Okay, I'm to construct a suitable. Okay, so do you want an energy cycle? It will allow you to calculate the enthalpy change for. So do you want the enthalpy change of MgSO4 for this reaction? So do you want the enthalpy change of the reaction, which is. Sorry, by the way, we're just reading it now for you not to get confused as well. Wait. Alright, so basically here they gave you the enthalpy change of solution for the hydrated MgSO4, so you should know this. Okay. Alright, so we need to construct an energy cycle, so basically you want to put something here so you could put the hours or whatever. So we need something that will bind this side and this side, so we will be able to construct a cycle. So let's check MgSO4 plus 7 H2O. Okay, MgSO4 plus H2O. So basically what happens here is, like the first thing they said, that MgSO4 was added and stirred until it was completely dissolved in H2O. So what happens here basically, that MgSO4, which is solid, because it's an ionic compound and a compound dissolves in water, so basically MgSO4 dissolves in water, so it will actually give you MgSO4 not solid but aqueous. What does this mean? It means that MgSO4 is dissolved in aqueous, as ionic compounds are get dissolved in water. They do not react, by the way, they dissolve in water to give you its compound in aqueous. This means that they are dissolved, alright? And not reacted, dissolved, alright? So yes, you got an arrow, so now you have something that will relate to the other one. So in the first sentence they said the enthalpy change of solution of hydrated was calculated and found to be 9.60. So they give you that MgSO4 and hydrated form. It does give you as well MgSO4 aqueous, as they are the same reaction but in different experiments. So this gives you the arrow. So yes, plus 9.60. Right, now here we already have it. You found it here, the enthalpy change of the first equation or experiment, minus, please mention or write whatever the signs. They are very, very important because they will affect your answer. Alright, that's great. Now for sure they're still the same mark, so you should solve it to get the 1 mark. Crazy. Anyways, this is a full line. Basically go with the road, so there is an arrow here, it completes it. So you basically go like this. So this is 1, this line equals this line. So what you want to find, plus, as they are the same road, you could say, plus 9.60 equals, as let's say they are the equal thing, okay, this line equals this line, so you equal them, equals minus 85. Now you want to try to find for this again. So minus 85 will stay in place, so this will change to the other side. When you change the other side, charges will change as well, so it become 9.60. Now great. Minus 85, sorry, minus 85 minus 9.60. Yes, minus 94.6. Again, write everything in place. Got it. Hopefully understood. All right. And if you were confused by the arrow was going down, it's basically it's the same experiment, so they basically give the same answer, and you got the answer based on your knowledge and the resolving. Hope you understood. All right. Calculate the enthalpy change for the reaction. All right. Calculate the enthalpy change for this reaction. Go to sign in your answer. Well, this is funny because we already found it. Oh, I'm sorry. So I did not read the question carefully. So basically, this was your answer for the first part. This for this. So yes, that's great. So yes, 1 mark was for this. And by the way, equus is very important to show, or you won't get the mark, unfortunately. And yes, so you get 2 marks from this full solving. Hopefully understood. Question 3. The elements in pre-tree, NiMgAlPS, okay, whatever. They react in oxygen. So basically react them all with oxygen, and what will be the reaction when you form an oxide of them? Na will become Na2O because O has 2 minus, so for you to, if you don't know, cross multiply will become this answer. Mg, the same exact thing. Mg2 plus O2 minus, so they will cancel each other. P can either be, it's actually based on your preference, whatever you want. P for O10 or P for O6. So you write whatever pleases you, so I'm gonna go with P for O10. S is SO2 if you wonder how. S is 4 plus. O is 2 minus. By the way, it's a macromolecule. Cross multiply. S2, O4. Simplify them. SO2. Alright? Describe what you see. So do you want what you see? Sodium and sulfur are each heated, okay? And give an equation. So Na, whenever you see Na, you can remember that there are yellow flame. Alright? Please learn the flame color of the atoms, please. It's very, very important. Equation Na plus O2 Na2O, and important to balance. Alright. Okay. Now for S. This could be a blue flame. You can either write blue flame or white fumes as SO2 is formed. Anyways, equation S plus O2 to give you SO2. Hopefully it's understood. Now, part B. Place the symbols of the elements AI, okay, the appropriate row of the table, okay. So do you want which are acidic, which are amphoteric, which are basic, Okay, and they want symbol of elements, not the oxide, just elements. So, okay, P and S. P and S are acidic. Please learn them. Amphoteric is always, whenever we see amphoteric, always remember Al, aluminium. And basic are the metallic part, Na and Mg. Okay, supposed to be easy, hopefully. State the bonding present in acidic and basic oxides. Acidic, I want you to just always remember them. They could be covalents. Compounds or bondings, basic or ionic. Alright, write them down. Covalent and ionic. Great. Write equation. Okay, I want you to remember. You want the equation for reaction of aluminium oxide with each hydrochloric acid and NaOH. And now you wonder about it. Basically, as I said, aluminium is amphoteric. Amphoteric means that it reacts with both base and acid. That's why in this question you want for both aluminium oxide with acid and base. Alright, now Al2O3, which is the base of aluminium, plus HCl. Now we talk about the acid part. They give you AlCO3 plus H2O, and make sure to balance them. Since I'm looking at the mark scheme now, I can just do with them easily. Right? Or you can just learn the equation. Alright? But if something that you should learn is to learn the equation, alright? And then if you have time, also remember the numbers. If not, you can do them later in the exam. But what matters is to remember the letters or the equation. And that's for acid. Now for base. Al2O3 plus NaOH. And now when you talk about base, you should always add water with it. If you ask me, I don't know why, but you should always add water. That's why you should learn this equation. To give you now also this part is unfortunately learning. Alright, so please just try your best to learn this part, alright? Basically Al2O3 plus the base plus H2O, I should always add H2O to give you this compound. Please just memorize it. NaAlOH4. And if you wonder how did that came from, I wonder too. Na plus Al3 plus, then you have OH. So I wonder. So 1 plus 3 is 4. And this minus, so I said they cancel each other. They give you this. And yeah, just learn this piece for me. And now we still need the balance again. Alright. So please, important. Alright, explain how the presence of the impurity in fuels can give rise to acidic name of a purity. Impurity here could be sulfur. You could say sulfur, which is SO2. Maybe you could say since S plus O2 to give you SO2, and then basically what happens, SO2 will react with water to give you H2SO4, and in the mark scheme it also has H2SO3. Hopefully understood. Okay, now we're in organic chemistry part. Halogen alkane are useful. Alright, so we're talking about bromobutane reacts in 2 different ways with sodium hydroxide depending on the conditions. Now again, bromobutane is an halogen alkane. Halogen alkane can react in 2 ways. Can either be um sorry alcoholic base or aqueous base. Alcoholic base will end you up with an elimination reaction, and aqueous base will end you up with a nucleophilic substitution reaction. Great. Alright. When one is okay, we talk about aqueous again. Aqueous is nucleophilic substitution reaction. With aqueous sodium hydroxide, tribromethane produce an alcohol. I forgot about this part. Yes. So this gives you an alcohol as a product, like from hydrogen alkane into alcohol. This gives you hydrogen alkane into alkene. That exists as optical isomers. Optical isomers are basically a chiral carbon with different groups attached in each side. Sorry, was so wrong. Alright. Alright. Give the name of the mechanism for reaction between 2-bromomethane and aqueous sodium hydroxide. Oh, I said. Let me just repeat it again. Nucleophilic substitution reaction. Explain that the alcohol produced exists as a pair of optical isomers. As I said, okay, optical isomer is a chiral carbon. A chiral carbon, or a chiral carbon, or chiral center. Sorry, I was looking at the Mars game. I'm sorry. Chiral carbon or center, which is attached to 4 different groups or atoms or chains. Alright, have I understood? Draw the 3-dimensional structure of the optical isomers of the alcohol produced in II. A butane, right? 2 bromo, so it's placed in the second carbon. Alright, let's complete the hydrogen. You can skip this part if you're bored. Or you're tired, because I'm sure you are. Chemistry is pain, but it's okay. We got this. Alright. With it is a nucleophilic substitution reaction, so you just get in mind that Br will be replaced by something. So what we have, the reagent here is sodium hydroxide, NaOH. What happens? Na becomes Na plus, OH becomes OH minus. Great. Great. Same thing in here. Br is more electronegative than carbon, so it will take its whatever they're sharing together, so it will, the Br will go to become Br minus with an free lone pair, free pair, and then so we won't get confused. Wherever it goes, I don't know. Alright, so after, oh my god, I removed the entire thing. Alright, so after the Br gone with its pair, so it stole the one electron of carbon, sadly, so it becomes a carbon cation. So carbon cation now can now attract any negative charge ion, which is in this case the OH. So OH is so kind, it will be like, hey, I'll give you one of my electrons because I'm nice. So it will go. No, happy ending. There's an OH bonded. And if one cannot complete, Br minus will be now, you know what? I want to be kind now, so I'll go to you. They give you an ABr, which is the inorganic part, but we don't care about it. We care about this part. This is the OG. Now, do you want an optical isomer formed from this compound? So yes. This is a carbon which is connected to H. It's different. CH. A different group as well, OH. Different group as well, and this entire thing. So yes. Now you put them in a 3-dimensional shape, or you'll be done for. Put the carbon, the center one. Put an H. Now you can put in any, like you can put the shapes in any way. To be honest, but what matters is, I'll show you it later, but wait a minute. And up is the long carbon chain, which is CH2, CH3. Alright? Now what matters here in optical isomers, they're basically mirrored. Like, you know when you look at yourself in a mirror, you're like this, right? Now, this. Organic chemistry, these two are two isomers. Alright? Same thing in this case is the mirror. So, sorry. This will be in here. Mirrored image. OH is literally here, so it will stay as it. You can, it's not actually important to make them like that mirrored, like in this part, but you can do it either way just to be honest with your marks. And yes, that was in this side, it becomes on this side. Just like put your palm now on the left side and flip it to the right side. Good job. Heating 3-bromobutane, with ethanolic. Okay, ethanolic sodium hydroxide. So we're talking about alcoholic base, which is ethanolic base, which is forgot it. Wow, sodium hydroxide. It's an elimination reaction, so I guess this must be the answer. Give the name of mechanism. Yes, the mechanism here is elimination. Elimination. Great. So what happens again? You can skip this part. I'll try to be quick either way. Okay, since you know that is an elimination reaction, means you eliminate something. And as I told you, like the answer here should be alkene, so you should know that you should eliminate like two stuff, so there will be a double bond. Okay, so I got you got the answer. So you eliminate the Br and whatever H you want. Like, no, whatever H is near the halogen. Eliminate Br, yes, and any of the H near it. So you either can eliminate Br with this H, or you can eliminate Br and this H. Okay, you can't eliminate like this H. No, it should be whatever H near the halogen, which is in this case Br. Either Br this, or Br with this hydrogen, or Br with that hydrogen near it. Alright, So when you remove them, if you remove, let's say, remove this part with this PR, so it'll become like that. As I said, it's an alkene formed. It's an elimination reaction. So you remove the Br and the H is an elimination. So yes, now draw and then name the structure. Okay, now another important thing I just noticed that in this case, in this case, remove the Br and H like in this side to give you a double bond in here, right? So the double bond is between the middle. But if you instead remove the Br with the other hydrogen, instead the double bond will be here, right? So now this type of molecule will not form a geometrical isomer, because geometrical isomers are C double bond. For example, let's give you an example. CH3H. CH3H. Now geometrical isomers could be cis and trans. Now in this case it is cis, and trans could be same exact thing, but instead of this, you'll see the difference now. This is trans. So geometrical isomers have two types, cis and trans. Cis is basically the heavy groups are in the same side, which is the upper side, and the small ones, the lighter ones, are the down sides. Trans is the upper side is one heavy and one light, down is one heavy and one light. Alright, but in this case it's a problem. Why? Because if you want to write them in an H shape, because geometrical isomers are basically written in a H shape, you know, H shape. If you wrote this one, if you draw this one, in an H shape, there will be a problem. Alright? So this entire thing, CH2, CH3. Oh, that'll make you confused, I'm sure. Now, does this work the same thing as this? No, because I told you that you can't have, like, in this side both hydrogen. If they both have both hydrogen in the left or right side, or both have CH3, like if both have the same exact thing, it won't be working as cis and trans, so it won't be geometrical isomer. So in this sense it have the same thing in the left or right side, so it's wrong. Get it? Now, why the other one is correct instead, if you instead made an elimination of this side of the hydrogen, not the other one. Sorry? Okay, so instead if we move the Br from here and the H from here, so you have the double bond in between. So if you want to give it the H shape, CH, so you have an H up, CH3 down, H up, and the other side CH3 down. So this is exactly how the geometrical isomer work. Not the thing the same sides, it is completely wrong. It should be left and right should be different. Alright, so it will become C, CH3, H, CH3. And now quiz time. Is it cis or trans? I said when the heavy groups, all the heavy groups are down, and all the light groups, in this case or H's, are up, cis. Alright? They are the exact same thing, by the way. Okay? When the heavy groups are in one side, up or down means it's cis. And if like one is heavy and one light in the same upper side or downside, mean they are trans. Great. Now just so okay, so you choose this one, please. Not this is wrong. Oh wait, so I'll write it down because I already explained it for you guys. The naming, I will help you in it. Just let me just write them down, please. CS3. Okay, again guys, with me. When the heavy sides are up or down, same side means they are cis. And when one is light, one is heavy in the same side, they're trans. Now this will help us in their names. Now, first thing before, we have one carbon, second carbon, third, fourth. So there's bute, alright? So there's an alkene, there's a double bond. And the double bond are in the 1, 2. Double bond is present in the second carbon, so it's bute. Bute for the number of carbons. 2 is for where the double bond is present. Double bond is present in here. Example, if the double bond was present in here instead, it's for the first carbon, so it will be bute 1-ene. But in this case, double bond is present in the second carbon, so it's bute 2-ene. No, but that's not the end. I said again, this is a cis. Cis bute 2-ene. Now this is the exact same thing. You have 1, 2, 3, 4 bute. The double bond is present in the second carbon. 2-ene again, and this is not the end. This is a trans. So right, so you should specify whether it's trans or cis. And now you have, these are counted as 2 isomers since they come in paper 1 always. Right, so yes, cis and trans for geometrical isomers are counted as 2 isomers. For the optical, the inverted ones are also counted as 2 isomers. These are 2 isomers. Even though they're the exact same thing, but they are mirrors, so they are counted as 2 isomers. Here are also 2 isomers, cis and trans. Alright, that's exactly what I explained in here. Get it? Now, bute 1-ene. So bute 1-ene is what does not work as a geometrical isomer. Why? Because 2 H's on one side of the double bonds. So on geometrical isomers, you should not have a carbon with the exact same thing in the left or right, so it won't be working. So you can't like flip them to have like one light up, and one heavy up and one light down. In this case, yes, so it won't work, or like you will have like one light up and one light down, so it's completely wrong. Get it? So that explains this. Alright, part B. Okay, for this part, I don't think we still have it in our current Cambridge, because I really don't know this, so I highly believe that it's not here. Because the written mark scheme, it says for part I, there's propanoyl chloride, which I remember it being present in the syllabus of today, so we will cancel this part, unfortunately. Name the type of reaction involved in reaction 4 to just a suitable reagent. So you can see that it had the carboxylic acid at the beginning. They come on OH. So when it becomes from COOH to an OH, or from COOH to an aldehyde, then aldehyde on OH. So basically reducing in the functional group, so reduction happens. Alright? Now a reducing agent, you can use, in this case, LiAlH4 because it's a strong reducing agent, okay? Hopefully understood. State the name of a salt catalyzed for reaction 5. Alright. We had an OH group here. So you should wonder, what was the compound here that we added HBr to give you 2-bromopropane? OH should be removed. How? So I'll do it for you guys. Alright, draw it. Is this. So you want to add HBr. So how will you add HBr? So I'll think, what if I moved an H and OH and H2O, and after you moved an H2O, the product that you will have is alkene, right? Okay, and then after you have an alkene, then you will be able to add an HBr. So then Br will become Br minus, and it took the bond paired from the H. It should become an H plus, right? And then what happened here is low-key very, very important. The double, like one of the bonds will react with H. Alright? So they will go here. The H will come. Now, since the double bonds, okay, look, since the H plus did not have any electron to share, so the whole entire thing, there was 1 and 2 electrons are now shared from this carbon, but this electron was from this carbon, right? So the carbon will be like, hey, I want my electron back. So it's now a carbon cation. So now carbon cation can now attract any nucleophile. So in this case, this nucleophile will be like, hey, I'll help you to be Br. And yes, this is your answer. Great. It is remove the water. So we need a dehydrating agent. So Al2O3 or concentrated sulfuric acid is a dehydrating agent, but in this case they said Al2O3. Al2O3 is actually very known to be a dehydrating agent to remove a minus H2O, so write it down. Al2O3. Alright. Production of, oh wow, the production of propane from Y. What is Y? Once again, because I truly forgot. What is Y? What is Y? What is Y? Oh. Alright. So the explanation came in handy. Wow. This is Y. Y is after the dehydrating agent. So it's an alkene. But I just added the BRs to explain you, alright? Alkene. Alright. So H. See what I explained you. But let's re-explain. It's fine. Who does not want to re-explain? Who does not want it? Alright. Okay. So again, what happens? The Br is more electronegative than H, so it will attract the electron pair to become. But I should actually first show this, that bromine is partially negative and H is partially positive. Alright, then what happens is after the H becomes partially positive, it can now attract any electron pair. So this will happen. So that's the first step. Now intermediate is when there is a carbon cation. So you should repeat everything after you added the H. Alright? Now complete everything once again. Hopefully you're understanding everything till now. I tried to explain everything in details, to be honest. No. Br minus now. The Br have fully gotten everything from it, so it's now a Br minus with a lone pair. Sorry. Electron pair. So a carbon cation form because the electron is fully to the hydrogen, so the carbon wants its electron back. The Br minus is cute, so it will give it. So yes, this is the final compound. This is great. Give the name of the mechanism in VI when you always have a reaction with an alkene. And alkenes, they never share anything. I mean, alkenes never substitute anything, so it's always addition reactions in alkene. And to specify more, it's an electrophilic addition reaction. Okay? All the reactions of alkene are basically electrophilic addition. Alright? 1-bromopropane is a minor product of reaction 6. Why 2-bromopropane? Okay, the difference is a bromopropane 1 is where the bromo is bounded to the first carbon, right? Let's complete this so you guys won't get confused. It's okay. This is the minor product as whatever they said. Why we'll be explaining. Okay? Now, instead you have now B2-bromopropane, so it's basically bounded to the second carbon. Okay. So what will you notice? This Br, the Br is connected to the carbon at the very end. So do you feel like when you're sitting with your friends in a couch and you're sitting at the very middle and there's some huge ass people sitting at the sides, you'll feel safe, right? If this was you feel safe, hey, I'm safe. But what if instead that was you? You're bounded to anyone to attack you and jump you and kill you. So that exactly what relates in here. The C is at the very end, so you're very prone to damage. BR is it's between this bodyguards. See, these are bodyguards. So yes, you're safe. That's why I'm gonna call this major. A major product. I guess this explains it all. Right? So yes, basically when you add an alkene, you can either add it, okay, I'll explain this again, it's okay. When you have an alkene, you can either add the bromine here to give you the major where the bromine is at the center, or you can use your big ass mind, because you have free will, right? You can either put the BR here to give you 2-bromo, which is the major product, is the safest one, or you can put the BR at the very end at the minor one, because you want to face challenges in your cooking, and you will so prone to damage, but okay, you want it, so your life, your rules. So yes. So the difference is secondary carbon cation, because like before anything there was a cation, I told you. So yes, this will form, sorry, the charge was low. Anyways, this will form a major. Why? Because the Br is at the center. This Br is connected to the carbon, which is the center, so it is the safest option. So this is major. So why we say secondary carbon cation is more stable than primary, means that the secondary carbon cation, this is the carbon cation, which is the secondary because it's bonded to, because the Br is bonded to this carbon, right? And this carbon is bonded to one carbon chain and one other carbon. So in the halogen or something is bonded to the carbon, this carbon is bonded to one carbon, and another carbon, it is called secondary carbon. And why we say cation? Because cation is getting the charge. Okay, all right. And now more stable than primary cation means instead this. Wait a minute, please don't go yet. Trying to deliver the thing. This carbon is a carbon cation. And why do we say it's a primary? Because this carbon is connected only to one chain. In this case, this carbon cation is connected to one chain and a second chain. That's why we said this is secondary. But in this case, it's a primary carbon. Primary because the carbon is connected to one chain only. Because if there was a carbon here, it means it's secondary, but in this case, it's only one carbon chain. Carbon cation indicating the charge. Okay, this one mark. Second mark, due to what? Like what happens due to electron releasing in this? Okay, please just memorize this answer. Or positive inductive effect of alkyl groups. Alkyl groups is basically what are they bounded with. Okay, all right. So the second mark is only, and I want you to memorize it, please. Okay, you can say due to electron releasing character or positive inductive effective alkyl group. But I think that's more alike, so learn this one. To be honest, it's more like it. It's actually it's easy. It's the inductive effect of what this stuff, of what the bodyguards do to the queen, which is this. Basically, we're talking about the C. Yes, there was a full past paper, and it was tiring, to be honest. It was a strong one, I'm not even lying. But yes, thank you so much for your time.